Hello everybody. Today we're going to be talking about the best practices for designing a distillation and absorption column. My group consists of Tariq, Adam, Kyle, Jesse, Mary Ann, and me, Jerry. Distillation and absorption. It's a separation of a liquid or vapor-liquid mixture. In distillation, it's based on the components' boiling points and volatilities. Here, a liquid and vapor phase is always present to allow the contact between them. It uses the application and removal of heat to do the separation. Absorption is similar to distillation in a sense, but it's based on the component solubility. Here, a liquid or solid absorbent is used within the column to dissolve the feed stream into a liquid stream. Distillation columns. They are vertical cylindrical vessels. As you can see inside the picture, there are external devices that are part of the distillation column to allow it to work. How it works is that a feed stream comes in and will either rise or descend depending on the phases. A liquid will descend towards the bottom while a vapor rises towards the top. A reboiler is used to evaporate the liquid stream into a vapor, while a condenser is used to condense the vapor back into a liquid to either be collected. There are internal devices within the column, and they are trays and packings, and this presentation is going to elaborate more on that. The first type of distillation column are tray columns. As you can see inside the picture, there are trays that are equally spaced within the column. Here, the contact of the phases are in steps or stages. How it works is that it retains some of the liquid, but still allows it to flow down with gravity, and also allows the vapor to rise towards the top to provide the contact. The second type of distillation columns are packed bed columns. Instead of trays, it uses packings. In here, it allows for the continuous contact of the two phases. These two types of distillation columns have different characteristics, and this presentation will go more into detail about it. And now, Kyle will talk about how to pick between a tray or packed column.
How do you choose between a tray column and a packed column? Well, there are several criteria to consider when making this decision. For instance, the ranges of operation for vapor and liquid flow rates are important to consider. In general, the tray columns tend to operate well over a wider range of liquid and vapor flow rates than the packed columns, especially at lower liquid flow rates. As for the liquid distribution, it is very hard to get an even distribution of the liquid phase in a packed column compared to a tray column, and often packed columns need a liquid redistributor to keep even distribution, especially in columns of larger diameter. It is also important to consider providing for cooling or adding or taking side streams. It's easy to add or take side streams on a tray column because you can put in the side streams at specific stages, and cooling is easier to provide for because cooling coils can be installed on the bottom of the trays. Efficiency calculations tend to be more precise for plate columns than for packed columns because the calculation for the height of a theoretical plate, or HETP, for a packed column is not always exact, especially when dealing with random packings. It's also important to provide for installation, cleaning, and replacement costs and difficulty. With larger columns, more than, say, 2 feet in diameter, it's easy to get a maintenance worker access to the inside of the column, which makes it easier to work with a plate column because you can have a maintenance worker go in and install the plates, replace them, and clean them if they become fouled. However, with smaller columns, where there isn't enough room for a maintenance worker to access them for cleaning, it can often be cheaper to use packings and then replace them if they become fouled. Pressure drop can be important in certain situations, especially with vacuum distillation. Packed columns have much lower pressure drops in general than tray columns, which makes packed columns a wiser choice for vacuum distillation. Often, distillation and absorption can deal with many different types of substances. Some might be foaming, some might be corrosive, some might be hazardous, toxic, or flammable. Packed columns work well for corrosive substances because you can use a wide range of materials for packings, which makes it easier to find a corrosion-resistant material to use. They work well with hazardous liquids because of the shorter liquid holdup, which makes it easier to provide for safety measures. The packed columns also work relatively well with foaming materials compared to trays. And next, Tarek will be talking about the different types of trays.
Alright, so let's focus on trays right now. So the trays are categorized into two main categories of types of trays. And the first one you see on the left side is a counterflow tray, and the one on the right side is a crossflow tray. The differences between them are very subtle but important. In the crossflow tray, the liquid and vapor are flowing in perpendicular directions. That means the liquid is flowing sideways and the vapor is flowing downwards. In the counterflow trays, the liquid and vapor are flowing in the exact opposite direction to each other, and they're flowing through the same perforations. So this table over here summarizes the very common industry examples of crossflow trays and counterflow trays. As you can see, for crossflow trays, there's three main types out there, which is bubble cap trays, sieve trays, and valve trays. And in terms of counterflow trays, it's more of the state of the art, and it can be changed, and there's a lot of novel new technologies coming out. And as examples, I've placed dual flow trays, multiple downcomers, and baffle trays. Let's go into some of the specifics. So right now we have, let's look at bubble cap trays. So on the left side over here, you have a real-life photo of a bubble cap tray, what it looks like. On the right side here, you have a zoomed-in schematic of one bubble cap. And as you can see, the vapor flows down and in through the bubble cap and out through the liquid. And this forces the liquid to go through forces the vapor and the liquid to contact. And this increases the contact time and surface contact. Next we have sieve trays. Sieve trays are the most simple kind of trays, and it's just it's a sheet with holes in them, pretty much. And there's a downcomer too, but this diagram focuses in on the actual tray, and it shows the vapor flowing up through the perforations and the liquid being on top. Valve trays are kind of a fusion between bubble caps and sieve trays. They're kind of similar, except that the valve actually is movable, and it's moved up and down by the pressure of the vapor itself. So the vapor flowing up pushes the valve up, makes space for itself, and flows through the liquid, initiating contact. These are more common than bubble cap trays right now. Bubble cap trays used to be very common back in the day, but as of recently, they've changed the methods. In terms of counterflow trays, this is some of the novel examples that are out there right now. There's multiple examples, and there's proprietary examples too. So I'm going to talk about some of the most common ones. And on the far right, we have a schematic of a dual flow tray. A dual flow tray is a sieve tray without a downcomer, which means that the liquid and the vapor are both flowing through the sieve and flowing through the perforations, and there's no downcomer. And in the middle, you see a multiple downcomer tray, and there's a difference between a multiple downcomer and a single downcomer tray. As you can see, the single downcomer tray, there's only one downcomer per tray, and the liquid falls down sequentially. In contrast, the multiple downcomer might have 2 or 3 downcomers on one tray. And this creates a multiple pass system which increases surface area contact, etc., etc. On the far left over here, we have baffle trays. This is a non-perforated tray, and it provides minimal contact and low efficiency, and it's used in some special cases. And there's a curtain of liquid falling off the baffles, and the only contact that happens between the vapor and the liquid is when the curtain of liquid is falling down. Next, we have Kyle going to talk to you about the different kinds of trays and how to select between them and the criteria.
The three main workhorses of the tray column are the sieve, valve, and bubble cap trays, the crossflow trays. One of the important factors to consider is the cost of manufacturing and installing. Sieves are the cheapest. Valves cost roughly 1.5 times as much as sieves, and bubble caps are by far the most expensive at about 2 to 3 times the cost of a sieve. Efficiency is similar for the three types, the order from most efficient to least efficient being sieve, valve, bubble cap. Capacity is similar for sieves and valves, and a little bit lower for bubble caps because the bulky bubble caps don't provide room for as many pores per unit area. Pressure drop can be important with low pressure distillation processes. Sieves have the lowest pressure drop per stage, followed by valves being a little higher, bubble caps having the highest pressure drop. Vapor rate range is one of the most important factors. Sieves work well at high to moderate vapor flow rates so that there won't be weeping. Valves can protect against weeping a little better than sieves can, making them viable for lower vapor flow rates. Bubble caps should generally be avoided except at extremely low vapor flow rates, where a positive liquid seal is absolutely vital. In rarer special cases involving corrosive substances or fouling-prone mixtures, a counterflow tray column might be used because those tend to have lower maintenance costs, which makes it easier to deal with corrosion, and they tend to be more resistant to fouling. Next, Jesse will be discussing how to size a tray column.
When determining the size of the column, you should primarily focus on the vapor flow rate within the column. In general, you want to focus on the areas that you predict that flooding will occur, and you should size your column in about 20% excess of what you actually calculate. There are several methods to do this, which are listed here, but the methods primarily take into account fluid viscosity, density, along with the tray spacing and the hole diameter in the tray. And again, your main goal is to prevent flooding in the column. With hole area, you can choose smaller holes that are more efficient, but at the same time will cause a greater pressure drop, which could potentially damage your column. And also smaller holes could create fouling issues. While larger holes are less efficient, they are easier to maintain and will have less fouling issues. Some of the common sizing is seen here. Now Marianne will talk to you about material sizing, selection.
How do you choose materials for trays? There's two important components for selecting a tray: effects of corrosions and the cost. There's also three most common tray materials that various industries use: cast iron, carbon steels, and stainless steels. So let's talk about the effects of corrosion. For processes that we expect any corrosion, we use a stainless steel. For processes that we don't consider any corrosion, we use carbon steels and cast iron. For example, the separation with the water and acetone. We normally use carbon steels and cast iron. So let's talk about the cost. For cost, cast iron is more expensive compared to carbon steels and stainless steels. So next, Tariq is going to talk about the packings.
All right, let's talk about packing. So there are two major categories of types of packing out there. One of them is called random packing, and the other one is called ordered packing. And random packing, as the name suggests, is very random. You drop in different shapes of packing material into a column randomly, and it sets himself, and it creates surface area for liquid and vapor to contact on. And this table gives you a couple of examples like rings, saddles, and there's countless other shapes out there. And ordered packing is more of a structured material, and it's more like a metal corrugated sheet with different structures to them. Now, let me show you some examples and some images. So up here we have random packing, and these are multiple examples. These are just a few, and there's like countless examples out there in the industry, and there's novel new packing shapes coming out every day, better efficiencies. Up here you see something called Pro Pack, saddles, rings, balls, and other shapes. And I could go on forever about these. Ordered and structured packing, just to give you a quick idea of what they look like. They're corrugated metal sheets. They could be made of other materials too, but they're very ordered and structured, and they have kind of an array and kind of lattice involved in them. And these two different kinds of packings have different characteristics to them, and there's different reasons why you would choose them, and that's where Kyle comes in. He's going to talk to you about how you choose between random and structured packing.
How do you choose what type of packing to use? As Tariq mentioned, there are countless different types of packing available, and much of the comparing the strengths and weaknesses would involve experimental data. However, there are trends that generally hold true when comparing random packing to structured packing. For example, in cost, Random packing tends to cost substantially less per unit volume than structured packing does, which makes it a better choice if the packing needs to be replaced frequently. However, for efficiency, the significant advantage offered by structured packing over random packing greatly offsets the increased capital cost. HETP is another advantage of the structured packing because structured packing tends to have shorter HETPs, making it easier to fit more stages of structured packing into a column of a specified height. Pressure drop, as mentioned before, is a consideration for vacuum distillation, and structured packing provides lower pressure drops per stage than random packing does. Liquid distribution will be a problem for packed columns in general, but it will be a little bit less of a problem for structured packing compared to random packing, because with random packing, the orientation of the packing pieces will not always be in a predictable pattern. Next, Jesse will be discussing how to size a packed column.
So now let's talk about sizing packed columns. With a packed column, you want to aim for between 40 and 80% flooding, which means liquid in your system. This will allow optimal mass transfer. Above this number, above 80%, you're going to have total flooding of the column, and you'll have no mass transfer. The other objective of sizing the packed column correctly is to have good distribution of your vapor and liquid, and redistribution. One method to determine the height of the column is the height equivalent of theoretical plate. This method determines an equivalent packing height that is equal to the distance between a tray and a trade column. With this method, we can use many of the same techniques that we use for trade columns on packed columns. The column diameter should be sized so that you prevent flooding and you control for the higher low vapor velocity. Too high of a vapor velocity will cause uncontrolled or too high of pressures within the column. Another method to size the column is to simply take the height equivalent theoretical plate and use that number as the actual diameter of the column. There are several other methods available. Now Marion is going to talk to us more about material selection.
How do you choose materials for packings? There are 5 important components that we have to consider for choosing packings. These are effects to corrosion, operating temperature, cost, mechanical strength, and self-wetting properties. There are 3 materials that most industries use, which are the plastics, ceramics, and stainless steels. Other materials are carbon, porcelain, and clays. So let's go back to the important components that we consider when selecting packings. The first one is the effects to corrosion. Stainless steels and ceramics do have a high corrosive effects. Plastics do have a moderate corrosive effects. The second one is the operating temperature. For processes that requires high operating temperature, we use stainless steels. For moderate one, we use plastics, and for low operating temperature, we use ceramics. And the next one will be the cost. Stainless steels and plastics are cheaper than ceramics. And then the fourth one, we talk about the mechanical strength. Stainless steel do have a high mechanical strength, and plastic and ceramics do have a low mechanical strength. They are easily broken. The fifth one will be the self-wetting properties. Ceramics do have a high self-wetting properties, while stainless steel do have a moderate one, and plastics do have a low one. Self-wetting properties is important because it ensures that the packing stays wet in the distillation column during the process. So originally, ceramics is the most common packings that we use due to effects to the corrosion. But they are expensive, so nowadays most industries do use plastics. They're lightweight, and they do have a reasonable operating temperature. They also have reasonable effects to corrosion, and they're cheaper to use. So the next one, Adam will be talking about the cost.
All right, I'm going to talk to you about how you can go about pricing, making a study guide estimate of how much it's going to cost you to build the absorption tower or distillation tower that you've designed. You're going to take some of the design parameters that Jesse talked about earlier, such as diameter, height, number and types of trays and packing, etc. This is going to give you base cost estimates for the shell, auxiliaries such as platforms and ladders, and internals, packing and trays. And then we're going to look at a couple of equations that will give you the total tower cost for both types of columns. This slide gives you the correlation we use to determine the base price of a carbon steel shell, and then the bottom correlation gives you the auxiliaries, such as platforms and ladders. This will give you the base cost for a carbon steel shell. So if you want to adjust for different types of materials, you can use those cost factors in the table at the bottom. This is going to give you the estimated price of your trays. So this is for carbon steel valve trays. You can adjust for different materials using the cost factors in the table at the bottom. And again, you can see that in the correlation, it's a function of the diameter of the trays themselves. All right, and if you're going to use a different type of tray, you're going to want to use these cost factors. So for instance, the correlation provided on the previous slide gave you a cost estimation for valve carbon steel. We showed you how to do different types of material. This gives you correlations for different types of trays themselves, so grid, bubble cap, etc. Another factor you want to consider is the number of trays factor that it's required to use in the final equations which we're working towards. That's given at the bottom there. That's a function of the number of trays you determine you need. Okay, determining the cost of the packing is quite easy. You'll find a number of tables such as this one that will give you the price per unit volume for different types of materials. It's really easy. You just find the volume you need to fill and you multiply it by the cost per unit volume. And finally, these two equations will give you total tower cost. You can see it takes into consideration all of the parameters which we determined over the past few slides. You can see in the bottom equation the volume of the column is necessary to determine the proper cost. Okay, the correlations I just talked about were developed in 1981. They're pretty accurate, but they need to be adjusted for inflation and other things such as cost of materials increases. So we use the CEP-CI, that's the Chemical Engineering Plant Cost Index. And what you do is you find your the year you're trying to adjust from and the current year, or the most current year you can find. You take the ratio of the two index values. So you take the current value on top, the previous value on the bottom, find just multiply the ratio by the cost of the column you've determined for the past, and that'll give you the current value of your column. So thanks very much. That's all we have for you today. I hope that we helped you determine how to pick and design and price your distillation column.